Hello, it's Mr. Kaladi here. Today we're going to be going through lesson 4.1, which is all about free fall. This is actually kind of a tricky lesson. There's a few tricky concepts here. Make sure you spend a lot of time going through the slides, making sure you understand these concepts. First is the difference between mass and weight. They aren't the same thing. The second is that a bathroom scale measures the normal force, not the force of gravity, and that's going to be important when we look at the two problems later. Finally, this is the kind of big misconception that comes back on your exam every year and students always get wrong. It's that when astronauts are floating on the space station, they're still experiencing gravity. I mean, the space station is still very close to Earth. There's still quite a bit of gravity. So the reason they're floating isn't because there's less gravity. They're floating because they're falling. They're in free fall. You know the feeling of free fall when you go on a roller coaster at Canada's Wonderland. That sinking feeling you get in the pit of your stomach as you go down the hill, that's free fall. The astronauts are in free fall all the time, and you kind of have that video that you can watch in this picture here. The only thing is that they're falling around the Earth, so the space station is constantly falling at the Earth, but it's missing it, and so in essence it's falling and it makes an orbit around the Earth. So just make sure you're aware of that kind of difficult concept. Okay, so let's look at these two examples. Jerry, who has a mass of 72 kilograms, stands on a spring scale. Jerry's friend George pushes down on the scale with a force of 12 newtons. What reading does the scale display? Remember what we said on the back of the last page? The scale doesn't actually measure your force of gravity. It measures the normal force. So if we want to draw a picture of the scale, free body diagram of the scale, we have we have the force of gravity from Jerry, and we also have the force applied by George, and then there's some sort of normal force. So let's just make a note here for the scale. Oh, there we go. Okay. Now, because the scale is not moving, we know these have to be balanced. So we know that Fn plus Fg plus Fa equals 0. For the purpose of this question, let's define down as positive. So Fg is equal to the mass times the gravitational constant, which is 72 times 9.8. Oh, I forgot my calculator. Let me just get that. Okay. So we have 72 times 9.8, and that gives me 705.6 newtons down. And then we also have the force applied, which is 12 newtons down. We should note that these are going to be positive when I put them into that formula because we've defined down as positive. So now I end up with Fn is plus 705.6 plus 12 equals 0. So that gives me Fn is equal to negative 717.6. Therefore, the scale reads... Oh, significant figures are tricky here because this is 2. So this has to be limited to... This number is limited to 2. So it'd be 7.2 times 10 to the 2 newtons up. So essentially, his weight is 705, but because his friend's pushing down on the scale actually outputs a higher number, right? 717. It makes him look heavier. Okay, let's continue on to example 2. In example 2, we have someone on an elevator, and these can be tricky questions, so we have this slide here. Again, you know the feeling of free fall. This is when you're on a roller coaster and you suddenly drop. You feel that weightlessness that you experience as you're falling. But you also can kind of imagine when you get in an elevator and it starts going upwards, you kind of feel like your legs are heavy, like you weigh a little bit more than normal as you accelerate upward just for a split second. Similarly, when you're in an elevator and it starts going down, you feel that falling sensation for a split second. In this case, you actually become, as the elevator accelerates upward, you have a slightly higher weight. This is like the guy pushing on the scale. You become a little bit heavier on the scale. And as you accelerate downward, this is the opposite. You become a little lighter. You can imagine the scale, which normally shows your weight, is for a split second going to show a smaller weight. Now, as you're moving at a constant speed, or as the elevator is at rest, well, there's no acceleration, so your weight is going to be normal. So Jerry goes on to, with his mass of 72, goes on to an elevator with a scale. He's weighing himself, and then suddenly the elevator starts accelerating down at 1.8 meters per second squared. What is the reading on the scale? So if he's going downwards, again, we're going to expect that there's that falling sensation in his stomach. He's going to go up slightly, so the scale is going to be a little lower. The number's going to be a little bit lower. Let's draw a free body diagram for the scale. For the scale. Gotta get a new pen. Okay, so there's the force of gravity acting on the scale by this person, or by Jerry. And then we know that there's going to be a normal force produced by the scale. So that's something like this. Now, are these the same length? Well, no, we know they're not, because we know that F net is going to be slightly down, right? Because we know the acceleration is down as well. When we add these up, this one, the gravity should be, the Fg should be longer than this one. Can we figure any of these out? Well, because they're not the same, I can't figure out Fn, but Fg I can figure out, because Fg is equal to mass times gravity. So the mass of this person is 72 kilograms times 9.8. That gives me 705.6. Oh yeah, we just did that. But it doesn't help me find the normal force. However, F net I can figure out, and I can work backwards, right? We know that F net is equal to mass times acceleration. I know that the guy's mass is 72. I know the acceleration is 1.8 meters per second squared down. So I get 129.6 newtons down. So we have a situation where I know this plus this is going to give me F net. So Fg plus Fn is going to be F net. I know Fg is 705.6. Let's define positive as down. So this is going to be plus 705.6. This is going to be positive 129.6. And this is going to be 129.6. Okay, so now I'm going to subtract this from the other side. So I get Fn is equal to 129.6 minus 705.6. And that gives me negative 576. Therefore, the scale reads 5.8 times 10 to the 2 newtons up, the opposite direction, which is up. So again, look what happened. The guy's weight is usually 705, but he's accelerating downward, so he gets that kind of sinking feeling in his stomach. He's slightly lighter, there's less weight on the scale, so his scale rating is lower. So he's lost a lot of weight for a split second. Okay, and then there's one last concept in this section, which is all about not free fall, but terminal velocity. And this is, you'll see there's a video and there's an explanation. It's pretty straightforward. But basically, as you drop out of a plane, you have no air resistance. But as you go faster and faster, the air resistance builds up until eventually your force of air resistance, is equal to the force of gravity. And so you stop accelerating. You're actually just balanced now, so you're falling at a constant velocity. And there's some interesting videos for you to watch. So hopefully that section makes sense. Make sure you're comfortable with a lot of the conceptual ideas. That's because there's some challenging ideas in it. All right, thanks. Until next time.